My name is David Krebes, and this lesson is suitable for a second-year calculus audience. We will investigate the following. E to the power of minus x squared over 2. And then we'll integrate that with respect to x. This is important in statistics. What we're looking at here is essentially the area under the bell curve. Note that you cannot find that antiderivative using techniques of integration. However, if we take the improper integral, or in some sense the entire integral, where x ranges between minus infinity and positive infinity, it's a different story. We will show that this improper integral is finite and that its value is the square root of 2 pi. Let's give this a name. Let's call it I, keeping in mind that I could be infinite. Now let's do a little trick. We'll take I and we'll multiply it by a copy of itself. So I squared. Now x is what's known as a bound variable, or also a dummy variable, and that means we can use whatever letter we want. So instead of x, let's use y. So e to the power of minus y squared over 2, y squared over 2, e to the power of minus y squared over 2 dy. And now let's take this first integral here and move it inside the second one. So what we get is a double integral. We multiply together the integrands to give us e to the power of negative x squared plus y squared over 2 dx dy. And x ranges between minus infinity and infinity, and so does y. This dx dy is what's known as the area element. So strictly speaking here, we would have to fidget with this business with the integral signs, but we won't do that. We'll just take note that all we're doing here is integrating that power of e over the entire xy plane. That's all we're doing. So now let's switch to polar coordinates. So if this is the origin down here, this is the origin, then this up here is our area element. And this dimension here is dr, whereas this dimension here is not d theta. That's an easy mistake to make. It's actually r d theta. And that r will come in very handy. So rewriting this using polar coordinates, we get r dr d theta. That's our area element. And now the power of e becomes e to the power of minus r squared over 2, because x squared plus y squared is equal to r squared. And now r ranges between 0 and infinity, whereas theta ranges between 0 and 2 pi. Now let's take this entire inner integral here and move it past the d theta because it's independent of theta. So 0 to 2 pi d theta, and then that entire inner integral, we move it over to the right, e to the minus r squared over 2 power r dr, where r ranges between 0 and infinity. So we've just taken that inner integral and moved it past the d theta. This first definite integral here is easy. That's just 2 pi. Now for this second improper integral here, let's make the substitution that we've always wanted to make, namely u equals minus r squared over 2. So that means that du is equal to minus r dr. So this r dr here is just equal to minus du. So let's bring the minus sign out in front. And then we've got the integral e to the u power du. Now, if r is 0, then u is 0. So our lower limit is 0. As r tends to positive infinity, u tends to minus infinity. So our upper limit is minus infinity. Now, e to the u power is its own antiderivative. So this is minus 2 pi e to the u from u equals 0 to u equals minus infinity. Minus 2 pi. Now, as u tends to minus infinity, e to the u power tends to 0. And e to the 0 power is equal to 1. So 0 minus 1. So that's equal to 2 pi. And as you recall, what we've been looking at here is I squared. So 2 pi is I squared. So I certainly has to be finite. And now if you look at that integral there, you see that that's positive everywhere. So I can certainly not possibly be the negative number negative square root of 2 pi. So I has to be the positive square root of 2 pi. And we're done. So looking back over our work, it seems that this integral here, whose evaluation has been our aim, finds its natural home in the xy plane. And in any event, its value is the square root of 2 pi.